Welcome back to Applied Algebra and Trigonometry. Today we're going to be talking about graphs on the graphing calculator. Stop. Before you watch this video, please familiarize yourself with graphing on your TI-89 calculator. You probably have the titanium version. Make sure before you view this video, you look at these three videos: pre-calculus, using a calculator to graph a function. The second one is TI-89 Calculator 26, Graphs, Zoom Modes, and Tracing. And the third is TI-89 Calculator 22, Graphing Piecewise Defined Functions. These gentlemen did an excellent job of discussing your TI-89 calculator. I didn't feel like I needed to reinvent the wheel to present those concepts to you. So please see those videos before you watch this one. The second video in the list is rather long. However, it's covering zoom modes. There are lots of different options for zooming on your calculator, zooming in and out on a graph, and you will use them to your benefit in different situations. You will want to watch that entire video at some time. If you want to just watch part of it, get a rough idea of what's going on, move on to the next video, and move on to this one, that would be fine. And of course, you can always return to that video or any video in our course for review. I'm just going to do a quick recap of a few important steps when you're graphing functions on the TI-89. First, always convert from function notation to XY notation if necessary. Also, if necessary, solve for y in terms of x. You want y isolated on the left-hand side to make it most like the way you're going to put it into your calculator. Enter the equation using the y equals key on the calculator, and then use the graph tool on your calculator. Let's take a look at example 1. This is the function f of t that is equal to 4 minus 0.5 times t. Let's change this to xy notation. Here's our dependent variable y. I'm going to go ahead and put this into our slope-intercept form, where the independent variable comes first with its coefficient and any sign connected with that coefficient. And then we have our constant. All right, now it is in the format in which you will see it in your calculator. It will just be slightly different. Let's make this y1 equals negative 0.5x plus 4. And now I'm going to show you how it looks when it's in your calculator properly. Here is how this equation should look in your table of equations. As you see, it is checked and ready to graph. Let's look at it. And here is our function. Now, what are the domain and range of this function? This is a simple linear function. The domain and the range are both all real numbers. Here is our next example. It is not in function notation, so we don't need to convert it to xy notation, but we do need to solve this for y. So if you examine this picture closely, you will see on the bottom row how I entered the function into the calculator. And notice it does have function notation in that lower bar. It's y1 of x equals what follows. Notice how it changes in format when you hit enter. It goes into what we call pretty print. It's basically the way you would write it, except for that dot between the -2 and the x squared when you are writing the problem. Okay, that's what we're going to graph. Let's do it. Now we have a graph that, although it does not appear to have anything that limits its domain, there is definitely a high point in the range, a point beyond which we cannot go and still be on the graph. So what is this y value? Well, let's check our window. If you check the window, you will see that this is a window that ranges from -10 in the x direction to +10 in the x direction, from -10 in the y direction to +10 in the y direction. So what is this? 1, 2, 3, 4, 5, 6, 7, 8. That is the point 0, 8. All right. Those are really small though, and if you are trying to do this on your calculator, it's sometimes hard to count those. Remember, well, if you watch the entire video about tracing and zooming, you have a few different ways you can do this to determine what point is there at the maximum value on this graph. To obtain this view on your calculator, you'll need to do an F3 trace. So hit the F3 button, which is off this picture down there, and you will find that your cursor blinks. Ask me how many times I had to take that picture before I actually got the cursor on camera. And here is the Y value for your cursor. That is as close as I can get it. I can get it just as close on the other side, but this rounds to 8. And doesn't that make sense? Because the X value on the Y-axis is 0, the Y value is 8. And if you plug 0 into the equation written above there, of course, you get Y equals 8. That is the maximum value that you will find on this graph. So let's state the domain and range. In this case, the domain is all real numbers and the range is all real numbers where y is less than or equal to 8. Here is our next function. I have converted it to xy form. It is already solved for y. So let's see what that looks like both as an equation in the calculator and as a graph. Please take a close look at how I entered the equation and how the calculator returned it and put it into the form you would use if you were writing the equation. All right, and then take a look at the graph. That's a very interesting graph. It looks like we have some asymptotes, but where are those asymptotes? You could do a trace on this to find them, but I would suggest using the table, the diamond F5, that will give you the table, and scrolling up and down through the table to see if you can find it instead. So let me move this graph out of the way a little bit and show you the table. Here's the table, and let me take just a moment to say don't get alarmed if some of your command functions seem to be scrambled. That's just because these functions do not apply to this screen. Another screen, when you get a little fancier with your knowledge of the computer, you will have those available to you when they're needed. All right, so here we have the asymptotes. -2 is undefined and 2 is undefined. Let me give you a picture of what happens if we go beyond 2. Now you see what happens if you move to the right of 2, the positive x direction. Your y gets smaller and smaller and smaller, which is exactly what it's doing on our graph here. Now think back to how we analyzed equations and functions. Will this function ever have a value of 0, or will it simply approach 0 in the direction of negative infinity and the direction of positive infinity? That is exactly what it does. So let's talk about the domain and range now. The domain of this function is all real numbers. X does not equal -2 or 2. And the range is all real numbers where y does not equal 0. But wait a minute, what is wrong with that answer? X and y were not in my original function. Let's state our answer with the original symbols. The independent variable was p. The dependent variable was m of p. Squeeze it in there. Here's another challenge for you. Stop the video, put it into your calculator, and see if you get what I do. You have my equation on the left, and there is my first attempt at the graph. But what's really happening there around the origin? Is there anything strange happening? Let's see. Yeah, zooming in here doesn't help, but let's use the calculator to zoom in. I chose to use a zoom box to get closer. It looks like it's going to go down and touch at 0, because if I think about it, and I put 0 in for x into my equation, I'd have 0 squared over the square root of 3 minus 0. I would not have 0 in the denominator, but I would have it in the numerator, so y would equal 0. But just to make sure I am analyzing this correctly, I'm going to take a look at the table. Now my table did confirm that as I was scrolling up and down, that 0, 0 is the lowest point on this graph. But as I continued to scroll, look at what I found when I got to 3. And in fact, if you had just analyzed this function without your calculator, would you not have seen that if you put 3 into that radical, you'll get 0 in the denominator? 3 minus 3 is 0. That's under the radical. Okay, square root of 0 is 0, but you're dividing by 0, which is a no-no. Beyond that, it does some strange things. So it looks like we need to zoom out from our original setting. Let me do that. So I zoomed out twice and arrived at this. As our table indicated, there is an asymptote at x equals 3, and you could find that by tracing or referring back to the table. But then you have this strange thing going when it's close to 3 from the positive direction, like 3.001, you are way down in negative infinity. As you move away from 3, it rises to a certain point. What point would that be before it goes back down? Referring to my table again, as I look at what's happening as I approach 6, this is very negative. It gets up as high as negative 12 and starts going negative again. And as I scroll more, that is what I see. Let's try a trace function on this. Okay, let's see what that y value down there at the bottom does as I move to the right with my arrow key. Well, the cursor disappeared off the top and came back on the bottom. Let's see how close I can get here. There's a negative 13.3, a 12.07, 12.09. That's down a little bit because it's negative. So somewhere in there is my highest point on the right side of my graph. Let's try a zoom box. Let's see. Oh, zoom box is number 1, so let me hit 1. I'm going to move up just a little bit above this. Okay, that's going to be my upper left corner. Come down and go across. So I really want to zoom in on this a lot and hit enter. There we go. Let's see if we can do a trace on this now. Oh, that looks nice. Let's just scroll to the left a little bit and see how high that y value will go, how close to 0, because we're approaching it from the negative 0.08, 0.05, 0.02, 0.01, 0.003, and now I'm going back down again. Okay, so it's not going to give me exactly that negative 12, but I did see that on the table. So I'm going to go with negative 12 there. So to find the domain and range here, I did some analysis of the function. I graphed the function, I zoomed in and out on the function, and I examined the tables, all to find the domain for this function is all real numbers, where f does not equal 3, and the range is all real numbers, where b of f is less than or equal to negative 12, because this goes down in both directions. It's less than negative 12, or b of f is greater than or equal to 0. So let's do an application problem now. Here we have a rectangular piece of sheet metal, 10 inches by 12 inches, and that is the total side from that edge to that edge, and the same with 12 inches. Okay, but from that 12 inches, we're going to cut out some squares. I'm not sure what length these cutouts are going to be, but we do know we want this storage bin to be able to hold 90 cubic inches. So how would we go about doing this? When we have cut out the squares, we'll have a storage bin, maybe like that. Maybe the sides will be taller, look taller than that, and the bottom will look shorter in 2 dimensions. But at any rate, however it works out, we're going to be multiplying the length times the width times the height. And we want this whole product to equal 90 inches cubed. We could perform that multiplication and get an expanded expression, but we're not going to need to do that for your calculator. We do need to do one other thing, though. In order for you to graph a function on your calculator, we have to get everything on one side of the equal sign. So what I'm going to do is subtract 90 from both sides. Because I want to use my calculator to solve this, I'm going to flip this equation left to right. Okay, see that? Even with modern technology, sometimes you just have to do it by hand. That's better. But it's still not in the correct form to put it into your calculator. We're going to write this as a function, not as an equation set equal to 0, in order to use your calculator. So in place of that 0, I'm going to put y1 or y2 or wherever it falls in that list. That will go on the left-hand side. Let me put that into my calculator and show you the graph. So here is the graph, and as you can see, there are 1, 2, 3 places where that graph crosses the x-axis. That will be where y equals 0. And those values of x are known as the solutions, or the zeros, or sometimes the roots of the equation. Your calculator refers to them as zeros. You can find those zeros by doing a trace of this graph, by going to the table, or by using the handy function I'm about to show you, or the handy tool. If you push the F5 button, this drop-down table will give you 0 as your second option, and that's the one you want. So now I'm going to walk you through finding the roots of this equation. All right, as you can see, it's asking you for a lower bound, and it's telling you your cursor is now located. The x value is 0.1265, whatever. It's really close to the y-axis, but that's way off our screen right now. So I'm going to scroll right until I can find that cursor. There it is. And it is located just to the left of the x value here where the graph crosses. So I'm going to set that as my lower bound by pushing enter. And now I need the upper bound. So I need a point just to the right of where it crosses the x-axis, and there it is. So I hit enter again, and it calculates for me that 0. So I have a 0 at 1.28, blah, 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 blah. Okay? And if you look at the y value, it's not exactly at 0 according to your calculator, but it's 1 times 10 to the negative 12th, which is really close to 0. You will be able to repeat the process fairly easily to find the next 0. The third 0 here is tricky to find because your y value jumps so much. It jumps from way down below the screen to way up the screen, so you actually have to zoom out quite a bit in order to use that 0 function to find it. But wait a minute, let's see if we really need to go to all that trouble. Since our first 0 is located at 1.28, I went ahead and numbered the x values to the right. So we'll see our 0 is between 7 and 8 units, okay, which would be 7 or 8 inches in what we're doing. But let's take a look at this. Even if it were only 7, by the time we did 12 minus 2 times 7, we would have a length for our longest side of -2 inches, which does not make sense. We don't have negative lengths. So this last 0 is not part of our solution, so we don't even have to find it. Yay! So here are our approximate answers. 1.28 inches will give you a box with these dimensions. While if we cut out squares with sides 2.39 inches, we will get a box that looks more like this with these dimensions. I hope you've enjoyed getting to know your TI-89 titanium calculator, your new best friend. We will be using it a lot during the course, and we will be practicing with it during class, so make sure you have it ready when we meet for our next class.